very accurately. And we have studied the thermal properties of the major end members, magnesium end members in the mantle. And we conclude that the local density approximation plus quasi-harmonic approximation reproduces very well the properties of primarily the thermal properties. Now, the elastic constants at high temperatures, the way we do them, and that gives us these elastic constants in a continuum, pressure and temperature, it's a little more demanding because we needed to obtain the equilibrium structure, apply strains, reoptimize internal degrees of freedom, and perform thermodynamic calculations, phonon sampling for each one of these configurations. And then compute the elastic constant. 10 pressures, 16 strains, approximately 6 to 10 Q points per configuration, 30 minutes per task per Q point on 32 cores. This is about 480 hours on 32 cores today. Yes, you can cut this time by a factor of 2 if you use double the number of cores or quadruple the number of cores. The scaling is not very linear here. But you can see how far, what the computational requirement is. If we are talking about solid solutions, obtain free energies of solid solutions, we need to sample a lot of configurations, and the thermodynamics starts to become very demanding. Okay, here are elastic constants of perovskite that we obtained in 2004, continuum of pressure temperature using the quasi-harmonic calculation. These black points were obtained by Arten and collaborators using molecular dynamics. And to me, the agreement was surprisingly good. I did not expect this level of agreement, but they obtained the elastic constants at a certain temperatures as in between 1500 Kelvin, 2500 Kelvin. And these points essentially fall in between the appropriate colored lines. The level of agreement is essentially outstanding, I would say. At this level, I mean, at the level of accuracy that we are interested. There are some deviations here that the source are still unclear to me. Perhaps Arten wants to comment later. But one thing that was very clear at that point, this calculation, it was that what was striking to me when I saw. So then we used a mantle geotherm and computed the elastic properties of the aggregate of perovskite and ferropericlase. We used some experimental data for ferropericlase. We did not use we did not know that ferropericlase had a spin crossover, and which I'm going to mention soon. But it was striking that the shear modulus in the bottom of the mantle was larger than the one we were calculating for pure perovskite or for an aggregate that we believe exists in the lower mantle. This was very, very striking to me, and no inelastic effect had been included. So we made a case in that paper that there was something, our model was incomplete. There was something else in the bottom of the mantle that we didn't know what it was, and it was causing this type of deviation. The shear modulus in the bottom of the mantle was larger than the one we could understand. And soon after, another phase was discovered. We received a private communication from Tokyo that a phase transformation in perovskite had been identified. The structure was not known when we received this X-ray diffraction. And with variable cell shape MD, baking and heating and shaking, we found this structure accidental. It was pure luck because this structure also could be described with 20 atoms per cell, and that's all we did. That was luck. And we came across this structure. We didn't know it exists with the X-ray diffraction was pretty similar. And this structure, we calculate the phase boundary between this was the first detailed calculation of first boundary as well. This type of calculation is not demanding. It's just two phases, and the computational requirement is the same as calculating thermodynamic properties, 50 hours per each one of these phases on 32 cores. That's all. So this was the first calculation of a detailed calculation of first boundary, testing of exchange correlation functional. And our phase boundary, the phase transformation at the pressures that was seen in the mantle intercepted the mantle geotherm, accidentally or not, at a conditions of the D double prime, top of the D double prime region. So D double prime region is this lower layer here in the bottom of the mantle. And so this was suggested. Someone in the Science magazine was in the audience when we presented this at the APS meeting and got interested in publishing this article. It was suggested here that this phase was the most important phase in the D double prime region. In fact, in some places, I think this is beneath the Caribbean. This is the type of discontinuity that is observed in shear velocity and longitudinal velocity. The jump in shear velocity is positive, and in longitudinal velocity, less positive, which implies that the jump in book velocity should be negative. And when we look at the jumping velocities in the shear, longitudinal, and book velocity at the phase boundary, this stripe here corresponds to the range of changing velocities across that stripe of the phase boundary that I mentioned, was indeed very close. Here is 1.75%, here is 0.75, and here was 2% and 0.5%. Close to the discontinuities that are observed in places where we should observe the post-perovskite phase. This was, the model was too simple to explain something of this nature, in my opinion, but this was a very important piece of information that I think it improved the credibility of this kind of calculation in geophysics community. We in the material science community, we trusted this. But in the geophysics community, I'm not sure there was much, this type of calculation was very credible. But this is a very interesting type of agreement. Okay. This is a real challenge. Elasticity of a phase like ferropericlase. One of the phases that contains iron is strongly correlated, and we need to go. This is a very demanding calculation. It was found in 2003 and 2004 that the phases of the lower mantle have this spin crossover. What does spin crossover mean, or spin transition? You start with iron has 6 electrons, 5 up, 1 down, and under pressure, there is a spin pairing phenomenon. And that iron ends up with 3 up and 3 down. There are anomalies associated with this phenomenon, volume anomalies, anomalies in the compressibility when this happens. And this has to be studied with a strongly correlated technique, and that's the point. We used the technique that will be discussed tomorrow by my colleague here in Minnesota. He is Matteo Coccoccioni. He is the developer of this method. You can calculate the LDA plus U by first principles, essentially. And it was important that we could calculate U as a function of volume, as a function of spin state, essentially as a function of everything. And there is there is a collapse in the volume of an oxygen octahedron when this happens. This is the charge density of iron in the high spin state. This is the up spin electrons, and this is one down spin electron in the high spin state. And this is the charge density in the low spin state. When this happens, there is a volume collapse of 8%. This happens, the compression curve has an anomaly when this happens. And it's not in a narrow pressure range, it's in a wide pressure range. Now, the calculation is not easy. The fraction of low spin states varies continuously as a function of pressure. And how do we calculate that fraction? Well, we have to minimize the free energy of the solid solution containing all spin states as a function of pressure and temperature to obtain that fraction. So we need a model a thermodynamic model for this system. We use simply here an ideal solid solution, and N is the fraction of low spin states that can vary as a function of pressure and temperature. The properties of this low spin phase and high spin phase can vary as a function of temperature. The compressibility has anomalies. The compressibility of the solids, of the ideal solution, has anomalies, and we needed to compute this quantity here, N. And there is also a formula for the compliances of the solid solution. The point is, what does it take to compute these properties of the N members, high spin and low spin, to build the solid solution? Again, we needed to compute free energies, do phonon calculations for the individual phases. So now we have two phases, high spin and low spin. And we need a model for the vibrational density of states, because at this point we still could not do phonons for strongly correlated systems. Now we can, and maybe Matteo will tell you about that tomorrow and what it takes. So we have a model for the vibrational density of states of high spin, low spin, and intermediate spin. It's a model based on first principles calculations. And this is N, the fraction of low spin states, as a function of pressure and temperature. As you compress, you go from high spin to low spin. This is high spin, low spin, fraction 1. It varies continuously and broadens with temperature. So these are some steps that are taken to compute the elastic constants of the solid solution, which I'm going to skip here, and I'm just going to show them and tell you what it takes to do this calculation. There are anomalies in the elastic constants, and that's because the low spin fraction changes the volume in a, as you saw, there is a transition between high spin and low spin volume. But what it takes, 10 pressures, 3 strains per configuration, and we have, the formulas are not important here. It's a model, but we have essentially 30 strains. Now, to obtain one struct equilibrium, you must, depends on everything. Must be calculated. It's structurally consistent and self-consistent. Each one of these calculations takes a couple of days for 60 atoms, 64 atoms on 256 cores. Couple days, maybe 2, maybe 7, maybe 1 week. So we have 30 of these runs. So you can start seeing what it takes to do this type of calculation. It's very demanding. Now, tomorrow, I'm going to show you a solution for this job deluge. I mean, a very large number of runs that can be pretty extensive. And that is the cyber infrastructure we developed called the VLab. We also started inspecting unharmonic effects on phase boundaries. This is the phase boundary between olivine and actually forsterite and wadsleyite, responsible for the 410 discontinuity in 410 kilometers depth discontinuity in the mantle. We have an uncertainty due to the exchange correlation. These are experimental phase boundaries. Our phase boundary has a Clapeyron slope of the quasi-harmonic phase boundary is 2.5 megapascal per Kelvin. But